this lecture is going to cover more alcohols. We've already done the intro to alcohols, which went pretty quickly because we've talked about alcohols a lot so far this semester. Now we're going to get into the reaction mechanisms of them and kind of what's going on. So the first thing we're going to talk about is acid catalyzed reactions. Excuse me. So when we talk about reactions with alcohols, we're going to focus first with the group 1 metals, the lithium, sodium, potassium, etc., and some of these other active metals. When we have these active metals, they form metal alkoxides. So we get the metal alkoxides, and basically all that means is that you'll notice when we had a hydrogen here, that got replaced by some metal. All right, so this is sodium methoxide. When we react with bases that are stronger than the alkoxide ions, then the alkoxide ions will convert alcohols down to salts. So if we start with an ethanol, we know it's an ethanol because it's a 1,2 carbon chain with the hydroxide on it. And let's say we used sodium hydride, which is a pretty strong base. When we react it with the sodium hydride, we're going to get sodium ethoxide. So we're going to get a hydrogen that comes off. This hydrogen is also going to come off. We're going to form H2 with it. And then this sodium is going to replace that hydrogen that's part of the hydroxyl group. Tertiary alcohols will react very, very quickly with the strong acids, hydrochloric, hydrobromic, hydroiodic. Remember, the tertiary alcohols is when there's a hydroxyl group attached to a carbon, and that carbon is attached to 3 other carbons. So if we're looking at this carbon here, it's attached to 1, 2, 3 carbons, and that's what makes it a tertiary alcohol. And what's going to happen is the hydroxyl group is going to completely kick off, and we're going to get a chloride ion or a bromide or an iodide ion attached where that hydroxyl group was. When we're looking at low molecular weight, water-soluble, primary, secondary alcohols, they are unreactive. So if you have a primary, secondary alcohol that is water-soluble, meaning it's polar, or a low molecular weight, it is not going to react under these conditions. Primary and secondary alcohols will react with hydrobromic and hydroiodic to form bromoalkanes and iodoalkanes. So if we have one butanol, here's my hydroxyl group to make it one, well, hold on, let me erase that. We got 1, 2, 3, 4. That's butane. The OH makes it a butanol, so it's one butanol reacted with hydrobromic, with water, and refluxing. Remember, refluxing is long, high heat. We're going to wind up with the bromine ion substituting for the hydroxyl functional group, and we're also going to get water. When we talk about secondary alcohols, we can get rearranged products, so we can get a racemic mixture. But the primary or major product is going to be where that hydroxyl group was. There is going to be formation of a carbocation. Anytime we have a formation of a carbocation, that's when we're going to get the racemic mixture. All right. So in this case, when we have a secondary alcohol where this hydroxyl group here is attached to a carbon that's attached to 1, 2 other carbons, it's a secondary alcohol added to HBr with heat, we're going to get a carbocation formation. So our intermediate will be this. And remember, there can be, oh, let me indicate that this is the intermediate there. Once the bromine comes in, the primary or major product will be where that carbocation was originally formed, but there can be a hydride shift. A hydride shift would mean we'd get this. Okay, and that's why that bromine can attach to that other carbon. We're still going to get water as a product. In primary alcohols, if there's a lot of beta branching, remember beta, it's up like a bird flies with the sky. When there's a lot of beta branching, you're going to get a lot of product from a rearrangement. So what does that mean? That means if this is my beta carbon, this is my alpha carbon, and if that hydroxyl group is on that alpha carbon, we're going to get a shift. There will be a hydride shift to satisfy that primary carbocation. When that carbocation is formed, here's my terrible drawing, y'all. Here's my carbocation. There will be a hydride shift to allow that bromine Okay, y'all get the idea. We're going to pretend that's all connected in my beautiful drawing. When we have that hydride shift, or in some cases a methyl shift, it depends on what we have present, okay? But if there's a tertiary carbon next to the primary, there will be a methyl shift. In this particular example, let me just rewrite. So we got, okay, let me just erase that. Okay, we would have a carbocation intermediate there. Because this carbon is tertiary, there's going to be a methyl shift. So what are we going to get? We're going to get this and the carbocation intermediate there. That's why this bromine will attach here. All right, once we get that methyl shift, it's doing that because that primary carbocation that's right here is not stable. It doesn't want to do that. Because that carbon happens to be tertiary just next to it, there will be a methyl shift. If it was a secondary carbocation, we would have seen a hydride shift. So let's talk about this. Chemists propose an SN1 mechanism for the conversion of a tertiary and secondary alcohol to haloalkanes by concentrated HX, whatever, could be hydrochloric, hydrobromic, hydroiodic, with the formation of a carbocation intermediate base. Remember, SN1 means you get that carbocation intermediate, where SN2 means it happens all at once simultaneously. We get a back attack of what we want to attach, while simultaneously the other thing is getting kicked off. So when we see this and we think this is going to happen, we're talking about relative ease of reaction of the alcohols. So what does that mean? Are we talking about a tertiary, secondary, or primary alcohol? We're also going to look at what happens with these rearrangements. So with our SN1 reaction of a tertiary alcohol, SN1 immediately should tell you, boom, carbocation. So the first thing we're going to do is we're going to add a proton to get our bromine ion. All right. So in this particular case, we're using HBr for our reaction. Okay, remember, it could be HCl, HBr, HI. In this particular example, they're just using HBr. So water's going to come in, attack this hydrogen. This hydrogen is going to be removed and goes to form a hydronium ion, and we get our bromide ion by itself. Now that bromide ion is ready to do something. Okay, it's kind of just sitting there on hold for just a second. The second thing that happens in step one is the proton transfer of the hydroxyl group. So we get the oxonium ion. So what in the world does that mean? That means if, for example, we're using 2-methyl-2-propanol or tert-butyl, the lone pairs from the oxygen are going to go and grab that hydrogen from the hydronium ion, leaving water by itself, and it's going to pick up this hydrogen. All right. When that happens and another water molecule comes in and grabs this hydrogen right here, the shared electrons go back onto the oxygen. This is a reversible reaction, and it happens very quickly. Reversible. It's happening all the time in solution. The second thing that's going to happen is there's going to be a bond breakage or cleavage of this right here. Remember, we need to form that carbocation. This is how the carbocation is formed. Once that oxonium oxide comes off, now we're left with the carbocation. And in this case, it's a very, very stable carbocation because that's a tertiary carbon. Water is a product. Here is our carbocation intermediate. There is no need for any shift of any kind. Frankly, there's nowhere a shift could occur. And a tertiary carbocation is the most stable. Third step. Now we got to form the new bond between the nucleophile and the electrophile. This is where the bromine comes back into the picture. The bromine is our nucleophile. Our carbocation is our electrophile. And the bromine is going to come in. It's going to attack that carbocation and form this new product. Okay? So with a tertiary SN1 reaction, summarize, first thing we got to do is break up to get our bromide ion while also forming the oxonium ion. Those two things are happening at the same time, and they're happening with the water that's in solution because these are aqueous solutions. Aqueous solutions means water is already present. We don't just say, poof, here it is. It's already in solution anytime there's an aqueous solution. So step one is form the bromide ion and then form the oxonium ion. That's happening first. Second step, form the carbocation by removal of the oxonium ion. That's where our water product comes into play. This is where we're getting our water product from. We've formed in this case, our tertiary carbocation. Now the bromide ion in step 3 comes in, attacks that carbocation, and forms a new bond between it and itself. That's where we're going to get the 2-bromo-2-methylpropane or tert-butyl bromide. Now, SN2 reactions, we're talking about with a primary alcohol now. Remember, SN2 means everything is happening simultaneously. Okay? So the first thing, again, is very similar to the SN1. We're going to form that oxonium ion. The oxonium ion has got to be formed so that the OH can completely come off. Once we have formed this oxonium ion here with a water molecule in solution, now a bromide ion is back attacking the carbon. And when that happens, that allows this oxonium ion to kick off. So what we get is we get the bromine attached to that primary carbon. The reason this can go through an SN2 reaction is because those primary carbons are so accessible and so easy to attack. By the way, this is our rate determining step, which means it's our slow step. Now, if we're talking about reacting with the formation of a tertiary carbocation intermediate by loss of water group and migration of the alkyl group, what does that mean? Shift. Alkyl shift. So let's look at this. Oh, by the way, this is when we're, I went too far. This is when we're talking about lots of beta branching. So again, first step, first and foremost, no matter what we're doing, SN1, SN2, we've got to get that oxonium ion there. All right. So first thing, add your proton to get your oxonium ion. All right. Now, this is where we're going to get our shift. In this case, it's going to be a methyl shift. Why do you think it's going to be a methyl shift? Look at the structure. Pause this. Think about it. When you unpause, I will give the answer. The reason we have a methyl shift is because here you have a primary carbon. That's what our alcohol is on, our hydroxyl group is on. the carbon right next to it, to its left, is a tertiary carbon. Seriously? We got a carbon that's attached to 1, 2, 3 carbons. So we're comparing a primary to a tertiary. As soon as that hydroxide group comes off, we now have a carbocation intermediate on the primary carbon. Okay, that's where it is when the hydroxide group or the oxonium ion comes off. Because of that, a tertiary carbocation or a secondary is much more stable, significantly more stable. So as soon as I do this methyl shift, what we're going to get is we're going to get that. Now we still have a tertiary carbocation. Why is it still tertiary? Because that carbon right there is attached to 1, 2, 3 carbons. Therefore, the tertiary carbocation is significantly more stable. That's what's going on here. Okay? So, when that shift happens, that's what allows this oxonium ion to be kicked off. When we get that, we get this here and our tertiary carbocation there. Now we have a much more stable carbocation than a primary carbocation intermediate. Once we have our tertiary carbocation intermediate, the nucleophile, in this case HCl, we're not using bromide ion this time. That's okay. Remember, it can be HCl, HBr, or HI. In this case, the chloride ion is going to come in, attack that carbocation, attach itself, and this is a very, very fast reaction. Remember, even though the tertiary carbocations are very stable compared to the primary, it still doesn't like to be a carbocation. So this nucleophile coming in to attack the carbocation electrophile will happen very quickly. So just an alternate method for what's going on, it basically has to do with what you're using. If you're using a very strong acid like HBr, HCl, HI, you are going to get that methyl shift. Or if it's a secondary, you'll get a hydride shift. But if we're looking at bromoalkanes from a primary and secondary alcohol, if we were to use phosphorus tribromide, rearrangement is much less. Okay, we have a much lower rate of rearrangement than if we used, for example, HBr. So if we compare PBr3 to HBr, we're going to get a significantly less rearrangement. It's going to happen, most rearrangements will happen with HBr. With the PBr3, not so much. Why? Because it pretty readily reacts and it'll go through pretty easily. It'll replace this hydroxide to form the bromide ion there, to form that new bond, and we'll get phosphoric acid as a product also. Now, where is that phosphoric acid coming from? Well, as soon as this phosphorus is gone, we wind up with Br minus in solution, and there's water in solution, so it's going to grab hydrogens from the water and from the hydroxyl group. So how does this reaction mechanism work? You have to remember that when we form an intermediate, we're going to get a really good leaving group here. That's a really good leaving group, all right? Oxygen hates being positive. If it can leave and go away and get rid of that positive charge, it will do it in a heartbeat. Oxygen is so electronegative, it does not want that positive charge. It can't handle it very well. So let's look at what happens. The lone pairs from the oxygen in the hydroxyl group are going to come in and attack the phosphorus. When that happens, one of these bromide ions will kick off. That's what forms this here, and we get a bromide ion in solution. That's step one. We're the step 1, new bond between the nucleophile and the electrophile. This simultaneously happens. As soon as the oxygen attacks the phosphorus, simultaneously one of the bromide ions is being kicked off. Doesn't matter which bromide ion it is. No, it does not. The second step is to form a new bond. All right, we're going to get a new bond between that bromide ion that was kicked off, and simultaneously, this is important, simultaneously, this excellent leaving group comes off. This is happening by way of SN2. When it's a simultaneous reaction, it's SN2. So the bromide ion is going to come in, attack the carbon. The carbon is simultaneously going to kick off that awesome leaving group. And now we have the hydroxyl group removed, and we have our new bromide ion attached. Now let's compare this to SOCl2 and SOBr2, thionyl chloride and thionyl bromide. Remember, this we would compare possibly to HCl and HBr. Now, I want to say one other thing. You'll note there was no rearrangement here because it's SN2. It's occurring in the SN2 reaction. That bromine can very easily come in and attack that carbon. Why? Do they give us? They do. Because this is very linear here. It's very open. This can easily be attacked right there. So if we're looking at 1-heptanol and thionyl chloride in the presence of pyridine, what we're going to get, again, is a chloride ion completely replacing the hydroxyl group. All right. We're also going to get sulfur dioxide and hydrochloric as a product. So this happens primarily with primary and secondary alcohols for the chloroalkanes. That's what we're going to get. If we want to go from a primary and secondary alcohol to a chloroalkane, the most popular is going to be thionyl chloride. Less rearrangement, significantly less, if not any at all. The thionyl bromide is we're going to convert our alcohols to a bromoalkane. So thionyl bromide, alcohol to bromoalkane. And we also are going to do this in the presence of pyridine or some other tertiary amine. A good example is triethylamine. All right, it's got to be done in the presence of these two things. Why? Because that's our catalyst for the reaction. We're going to get just enough alkoxide to neutralize the HCl or the HBr. Remember, that's what's formed. So it's a really good catalyst to keep what we want to attach to where we want it to attach, as opposed to forming something else. We get just enough alkoxide to neutralize this so it no longer wants to interfere with a primary reaction that we're trying to get. The primary reaction we're trying to get is to get rid of this and add this. If this is neutralized, it won't interfere with that reaction. Now, if we're talking about a tertiary alcohol, now we're talking about the reaction of an alcohol with thionyl chloride in the presence of a tertiary amine. Once we get this tertiary amine, we get stereoselective. What does that mean? That means racemic mixture. If one is wedged, the other could be dashed, etc. So if we have a wedged hydroxyl group, then our product with a tertiary amine, in the presence of a tertiary amine, is going to be a a dashed chloride. So if I had, I'm not counting right, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. If we had this, okay, then our product would be 1, 2, 3, 4, 5, 6, 7, 8, would be this. Okay, y'all get the idea. Okay? That's how this works. So let's look at this. Here's the reaction mechanism. The very first thing we're going to do is form the alkyl chlorosulfite. Well, Miss Merriweather, what in the heck does that mean? Well, what that means is that this oxygen is going to go ahead and attack that, and that's going to get kicked off. All right? So when the oxygen attacks the sulfur, one of these chloride ions is going to come off. Does it matter which one? Absolutely not. All right? In the real world it does, but for what you guys are doing, it doesn't. They're the same thing. One of them's got to come off. All right? We're going to form this alkyl chloral sulfite. We're also going to form HCl. Actually, let me change my colors here. Where does that HCl form from? It forms from the chlorine, the chloride ion that came off, and the hydroxyl group that came off. Okay? Now, the second step is what we call nucleophilic displacement of the leaving group by chloride ion. Blah, that's a mouthful. So what is really happening? Note that in this particular case, the original carbon is a secondary carbon. Okay? So we got a hydrogen in here that's partially positive, the chloride that's negative. It very easily and readily comes in and attacks that carbon. When that happens, it gets kicked off. So what does that really mean? If you look carefully at the arrow, it doesn't separate from the sulfur, right? What this means is when that bond is broken, the electrons shared between the carbon and the oxygen are going to form a double bond. As that double bond is formed, that's when your chloride ion gets kicked off. You get another chloride ion in solution. So in the end, you get your chloride ion attached to your secondary carbon. The oxygen, that's the first thing that you get. The second thing that you get is this double bonded oxygen with the kicked off chlorine. And the third thing you get is that chloride ion. All right, so when we talk about sulfonyl chlorides, these are from the sulfonic acids. Unlike sulfuric acid, they are strong acids. So, well, wait, Miss Merriweather, I thought sulfuric acid, H2SO4, I thought you said that was strong. Only the first deprotonation of sulfuric acid is strong. So only first proton removal, first deprotonation removal is strong. Okay? Now, the sulfonic acids are strong. So the sulfonyl chloride and sulfonic acid, very strong acid. It's an organic acid. That's why you typically don't see it on the list when you've studied Gen Chem 1 and 2. Well, specifically 2. So if we have sulfonic acid being a very strong acid, that means the anion of it will be a very weak base. And it's a very stable anion. That's what makes it a good leaving group. It is a weak base and a stable anion. Anything that is a stable anion is a good leaving group. Why? If it's stable as an anion, it can easily come off and be just fine in solution. If it's not a stable anion, then it doesn't want to leave. It doesn't want to be an anion. It doesn't want to have electrons lost and gained. So it's not a good leaving group. But in this case, because it's a weak base and a very stable anion, we get a very good leaving group. Okay, so sulfonate anion is a weak base, stable anion. That's what makes it a good leaving group. Some other commonly used sulfonyl chlorides are TSCl. So the here, all right, Y, also a good leaving group. Methane sulfonyl chloride, MSCl, also a good sulfonyl chloride. And when we talk about sulfonate esters, these are what allow us to convert a hydroxyl group, which, by the way, is a very poor leaving group. We need to use things that are pretty darn strong to get a hydroxyl group to leave. That's why we talked about the strong acids, HCl, HBr, HI, because the hydroxyl group does not want to leave. Why does it want to leave? Why does it not want to leave? It's not a good stable anion. What is the very first thing a hydroxyl group does in solution? Boom, it finds the first hydrogen it can to form water. It doesn't like to be alone. It's a needy leaving group. It likes its buddies. So we have to convert the very poor leaving group, the hydroxyl group, to a good leaving group, like tosylate or mesylate. Okay, those are really good leaving groups, and the sulfonate esters allow that to happen. So what's going on here? How do we form this alcohol to an acetate? The very first thing we have to do is break the bond or cleave the hydroxide bond and the retention of the configuration of the chiral center. This becomes important. What do we mean by that? That means we're going to break this bond and at the same time add this. Note they are both wedged. When they are both wedged, that means the configuration of the chiral center has stayed the same. We did not go from wedged to dashed. That would have changed the configuration of the chiral center. We maintained the configuration. So they both are wedged. Hydroxyl group comes off, OTS comes on, both in the wedged position. Oh, and look at that. Hydroxyl group, chloride ion. Guess what we get? Hydrochloric acid as a product. The second step is the nucleophilic displacement. All right, so the OTS is going to get gone by way of this particular sodium acetate. So what happens? It comes in, it displaces this by way of a back attack. Ergo, we go from wedged to dashed. Note now the chirality is different. The configuration of the chirality is different. So we get this back attack. So that's how we go from a wedged to a dashed.